Growing up, guys, I don't know if anybody else has had this experience, but I've always wanted to have a Mr. Miyagi in my life, an Obi-Wan Kenobi, someone who could see the potential in me before I even could. This is where our next speaker and I have something in common. We both had college professors who knew what we would end up doing with our lives even before we knew ourselves. Tom Sibley's college professors knew that he would be a math teacher, and he's been teaching math at CSB+SJU for 30 years. And what they didn't realize is one of Tom's college experiences that would one day ruin his campaign. When Tom was a junior in college, he was invited to a formal dinner. And all the men were told that they needed to wear a suit and tie. So, of course, Tom showed up wearing a bathing suit and a tie. And they let him in. Please welcome Tom Sibley.
Okay. Many people think mathematics is a strictly left brain activity based on calculation and strict logical reasoning, as opposed to the intuitive, artistic creativity on the right brain. But while math does involve lots of calculation and reasoning, it does involve intuition, especially past the high school level. And by intuition, I mean the ability to think holistically, to make insight of new connections between concepts and their relationships. However, intuition does not mean instantaneous understanding. That's another common mistake about math. People often think, oh, you just instantly understand math or else you're no good at it and you should move on to something else. That's not true. Some people are better than others at math, but everybody can improve their math abilities. And it takes commitment, hard work, but it takes intuition. Fortunately, there's a way to do that. And there's good. The good news is that intuition is possible. Benoit Mandelbrot said, intuition can be changed, refined, and modified. Mandelbrot is best known as the proponent of fractals, these wild curves and surfaces with swirls and finer levels of detail. For example, this Julia set shown here. Incidentally, Gaston Julia, the mathematician who figured these things out, did it almost 100 years ago. He had to do this long before there were computers to even make these images. So he had to figure out this and prove the theorems without ever seeing these things. He had incredible intuition to do that. My students need to improve their intuition, and it takes nurturing. It's not something that just happens naturally. So one of the things I want to talk to you is about how I do that. But I'm waiting for the next slide, of course. Somehow I got through that. There it is. Allow me an aside. I'm sitting on a class on art history this semester on modern and contemporary art. And when I was writing this talk, we were looking at Cubism. And I was amazed to find out that Georges Braque and Picasso spent a lot of time trying to build their intuition about how to make these artworks. And in response, people who view this art for the last 100 years have had to develop their intuition so they can get something out of modern art. Math students particularly need to work on intuition because math is so abstract. For example, in high school, they'd have one formula that applies to compound interest in a bank account or radioactivity on uranium. But math isn't about money. It isn't about uranium. It's not about anything. It's abstract. At the college level, it gets even more abstract. My students have to study vector spaces that are in 5 dimensions, or 500 dimensions, or infinitely many dimensions. And what counts is the structure. Mathematics is about the structure. But people don't think in structure. We think in meaning. So it's important that they make the link between the abstraction and their intuition, and they do this by building their intuition. I find the ideal place, in Mandelbrot's words, to change, refine, and modify students' intuition is in the geometry course for majors. I somehow got ahead of myself. There it is. Oh, no. There it is. Oh, yeah. Students come in with a pretty strong intuition of what they think ordinary traditional geometry is. And they're sometimes surprised and confused when they find out we're going to be studying geometries, plural. And in some of these geometries will flat out contradict all the comfortable truths that they thought they learned about geometry back in high school. For one of those truths that they feel pretty strongly about is about triangles, that every triangle has 180 degrees in their angles. And maybe you remember that too. So that actually was a very important theorem that was proven, is credited to Thales, who proved it 2,600 years ago in what we call Euclidean geometry. Euclidean geometry is named after Euclid, who wrote this fabulous book in 2,300 years ago on geometry, which contained everything you ever thought of was in geometry long ago. But there's a lot more going on. And where I start with them is with the idea of a sphere, something they think they know all about. I hand them basketballs from the basketball coach, and I have them draw triangles on it, and I give them a flexible protractor, and very quickly they realize, oh, the sum of the angles isn't 180 degrees, it's more than that. And with some reasoning and thinking out loud in groups, they come up with the formula, the relationship between the area of a triangle on a sphere and the sum of the angles. The bigger the triangle, the bigger the sum. And they can prove it. It's pretty neat how it works. Well, spherical geometry is just the start. We study a geometry so radical 200 years ago that the greatest mathematician at the time, Gauss, was afraid to publish his findings on it. He left it for two unknown mathematicians who published their stuff, and for 20 years, the mathematical world ignored them. They simply couldn't believe that this stuff was of any interest. When Gauss finally died, they looked at his notebooks and found out he'd done it. And since he was the greatest, they said, oh, this must be important. So they gave belated stuff to the credence to those two. So what was so radical about this geometry? Well, all they did was change one axiom in the geometry. The old traditional Euclidean geometry says, given a line, K, and a point P not on it, there's exactly one line through this point P that's parallel to the original one. This new geometry just changed it and said, well, who cares? Let's have more than one. Why not? That doesn't sound such a big deal. But it turns out that the consequences are really weird, and they get weird really quickly. 30 years ago, when I started teaching this geometry, my students found it really hard to understand this because it was all abstract. And they had very little intuition about this. So for the past 15 years, I've done something else. I hand them curved surfaces, this is a saddle-shaped surface, have them draw things on it, and within a half hour, they have made 3 to 5 conjectures about how this space works. And then we start developing this geometry theoretically, proofs, theorems. But we come back to these models every so often, and we run into the conjectures they've made, and we prove them. It's amazing how much intuition they have. They're able to do this even though at the start they had no idea what they were talking about, but they've developed an intuition. So, make sure okay. Then, later on we move to this other area of geometry called transformational geometry. On the right is, no, on the left, I guess, where you're facing, is this traditional Islamic pattern in Euclidean geometry. On your right is a hyperbolic pattern, and this is a Father Magnus creation. It's in spherical geometry, and the transformations are what underlies all of them. It's what makes them work, and we study that. By the time we're into this, they are able to prove theorems in all 3 of these geometries at the same time. That's an incredible increase of intuition. They're actually thinking in 3 geometries at the same time. You may think this is pretty weird and abstract, useless stuff, but it turns out that this kind of geometry was something that Einstein needed, and I could just read this quote. To this interpretation of geometry, I attach great importance, for should I have not been acquainted with it, I never would have been able to develop the theory of relativity. By the end of the semester, I'm able to show students that the mathematical space in which the theory of relativity takes place is a 4-dimensional combination of Euclidean geometry and hyperbolic geometry. And we can actually do those proofs. It's an incredible insight on their part to get to that point. The most important thing about learning is to learn to see with new eyes, to develop new intuition. Every discipline needs that, but especially mathematics. Thank you.